Okay, so in this, or maybe in the next couple of videos, I'm going to try and prove something that I thought was pretty difficult in, what do you call it, multivariable algebra, which is the inverse function theorem. So what the inverse function theorem, on multiple variables or n dimensions or whatever it is, at least in the versions given in lectures, it says that a function Rn, something like that. So these two dimensions are the same. If it's differentiable and the derivative is like non-singular, right? So the derivative at some point x of the function, this is invertible, right? So we can just say determinant is non-zero. In fact, we should just be more explicit. We should just say that its inverse exists. So we can write this. So this is a linear map, and then we have its inverse linear map. What the inverse function theorem says is just having this. I mean, there's a bit more to it, the way that it's phrased, but the basic thing we need to know is that if we have this, then f is injective, and therefore it's invertible. Okay, it's injective in some small neighborhood, around, and a small, a small open ball, I guess, around x, and close to x, let's say. And so that's what we're going to prove in the next maybe 1 or 2 videos. Because there's one thing I need to explain, right? There's a kind of trick that's used in this, and I think it's kind of alright. I think you'll just believe me. But it's the operator norm, right? So if you have some function, we can take the operator norm of it, and it's defined like this as a supremum of d of x, so value. And I guess the only thing you really need to know about this is that this thing doesn't go to infinity or anything, and it doesn't because d is a linear map. So and then we're dividing by something. So this if it was in one dimension, then it would just be like we're just doing a times x or something, dividing by x, right? The x's would cancel, and then this would just give us the operator norm was a or something, right? Anyway, but yeah, I don't think I will explain this. You can look it up. This is exactly the definition. Just see what happens when you plug in different d's or whatever. Like for example, if you plug in the identity map, right, then this will just give us x back, and then x divided by x would give you 1 for every non-zero x. And then we see that the operator norm on the identity map is 1. And at the same time, you can just do n times the identity, and then you get n times 1, which is n. Okay, so this is it for this video. In the next video, I think we might just prove the inverse function theorem, at least the way I've stated it here. There is a bit more. The inverse function theorem says that if this derivative is continuously, if f is continuously differentiable, that means the derivative is continuous, then this inverse I mean, we can already check that the inverse is differentiable, but it turns out the inverse is continuously differentiable. The inverse of f is continuously differentiable, and that's what the full inverse function theorem tells us, but we won't prove that because I don't know how. So see you in the next one.